Fast vector search is useless if it silently misses the right neighbors. FAISS makes the recall, latency, and index size trade-off visible. You'll walk away with a setup that chooses a search index by measuring recall, latency, and size. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Vector search is what happens when you turn text or images into numbers and ask which items are most similar. People reach for FAISS when a linear scan gets too slow or too large, typically when datasets exceed memory or you need sub-second queries. FAISS gives you optimized indexes and a practical way to trade exactness for speed and storage. The goal here is simple: a reproducible baseline and a tiny report that shows how many neighbors you keep, how long queries take, and how big the index is. At a high level, FAISS answers one question. Given a query vector, which stored vectors are closest by some distance? Exact search checks every vector and is easy to trust. Approximate search inspects fewer vectors, so it's faster and smaller. But you must measure what you lose. We'll use a small visual dataset so you can see the numbers before applying the same checks to real embeddings. We will build a minimal measurement pipeline. First, we create an exact reference index and collect true nearest neighbors. Then, we build a fast ANN index and compare its outputs to the exact answers while timing queries. Finally, we serialize the index and measure the file size so you can balance recall against deployment cost. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. To start, we need a simple, trusted reference that never drops neighbors. This snippet builds the smallest useful FAISS baseline for exact nearest neighbor search. Before tuning an ANN index, you need a trusted reference that does not skip candidates. The data is a simple two-dimensional line of 80 points, so the geometry is easy to see while still giving enough neighbors to test. FAISS.IndexIVFFlat L2 creates an exact L2 index, and exact.addXB stores every vector in row order. The visible output shows how many vectors FAISS accepted, which matters because every later recall score depends on this baseline being populated. Now that we have a ground truth index, we must capture the exact neighbors to compare quality. This example turns the exact FAISS index into ground truth for evaluation. ANN search is only meaningful if you can compare it to the neighbors you would have found without approximation. The three query vectors in Q ask for nearby points along the same line, and exact.search QK returns the exact top K IDs for each query. We keep those IDs in truth, so later snippets can score whether ANN search missed anything. The visible output shows the first query's exact nearest IDs, giving you a concrete reference before speed enters the picture. With truth captured, the next step is to build a faster path and measure what it gives up. This code measures what the faster FAISS ANN path gives up compared with exact search. FAISS.IndexIVFFlat partitions vectors into coarse lists, so search can inspect only part of the database instead of scanning all vectors. After and.trainXB learns the partitions, and and.addXB stores the vectors, and.nprobe equals 1 tells FAISS to search just one list per query. The recall calculation compares each ANN result row in GOT with the exact IDs in truth. The visible output shows recall below a perfect score, which is the miss neighbor trade-off most demos hide. That number is the single most important diagnostic for choosing an ANN. A single recall number is useful, But we also need to see latency changing with the quality knob. This snippet makes the FAISS speed versus quality knob visible instead of implicit. And.nprobe controls how many IVF lists FAISS checks for each query. With a lower value, search usually does less work and can be faster, but it may miss neighbors in nearby lists. With a higher value, recall can improve because more candidate vectors are searched at the cost of more distance comparisons and usually more latency. The loop times repeated and.search queue k calls with perf counter and recomputes recall against truth. The visible output shows the highest recall setting from this tiny sweep alongside its measured latency. Finally, we close the loop by measuring the storage footprint for the chosen setting. This example finishes the tiny FAISS baseline with a deployable concern: index size. A retrieval system is not chosen on recall alone, because the index also has to fit memory, disk, and deployment budgets. The code keeps the selected nprobe, writes the FAISS index with FAISS.WriteIndex, and measures the serialized file size with os.path.getSize. It then runs one final and.search q.k and recomputes final recall against truth. The visible output puts quality and storage side by side, which is the minimum report you need before choosing an ANN index. If you move this tiny example to a real project, treat the 3 query vectors as a small validation fold, and run the same sweeps on a held-out set of queries. Use the same report, exact baseline, recall numbers for each nprobe or index type, latency per query measured with repeated calls, and the serialized index size for deployment planning. This workflow gives you a compact, measurable FAISS checklist. Build an exact baseline, sweep ANN settings, measure recall and latency, and note index size. Use this when you need evidence to pick an index rather than guessing. One caveat: tiny example data can hide tricky geometry in real embeddings, so always validate on your actual vectors. A concrete next step is to tune FAISS nprobe alongside the index partition count on your data, and plot recall versus latency and size for a validation query set. That sweep is the single most practical way to pick an index that fits your deployment constraints. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.